fun people to work with. He was fearless, he was energetic, he would come in with new ideas that would challenge me, and it usually led somewhere really good. So it was a real pleasure to work with him, and I learned so much along the way. When he came here, he got me interested in a topic that I thought was really wonderful, the early part of my career, but I sort of put aside, which was the study of variable stars, stars that pulsate, and looking at their pulsation characteristics to really learn about the basic fundamental properties. And he got me interested, and it happened at an extremely exciting time when NASA had launched its Kepler mission to start looking at the light variations of stars in a part of the sky. They were trying to find planets that were transiting in front of the stars and looking for a small telltale sign of a planet. But at the same time, they measured these absolutely gorgeous, 1 part per million precision light curves for stars of all kinds. It just opened a new door in studying the pulsation properties of stars of all different kinds. So Zhao jumped right in at that stage and got very, very interested and wrote a wonderful dissertation looking at these. He studied in particular those stars that were members of binaries, where you can see the 2 stars go right in front of each other as well, and how their light curve changes as a function of their orbital phase. That gives rise to wonderful information about their fundamental properties, including their masses. If you look at time series analysis of the residuals from these light curves, studying the frequency component of the stars, which is probably what we'll hear about today, something about telling us about how their interiors work. And by looking at these pulsations, just the same as geologists use seismology to learn about the center of the Earth, we can use these same kind of ways to learn about the centers of stars and what their conditions are like. He went on and actually became a theorist as well, and was one of our first uses here of the MESA code to study stellar interiors and study stellar evolution. He followed that up with a very interesting code called Gyre, written by Richard Townsend at the University of Wisconsin, to look at the pulsation modes that were associated with the different kinds of stellar models. And then he introduced me to Bayesian statistics, something that he had been pushing for a very long time, and trying to see how one could use Bayesian statistics to study the spectrum of binary stars and find the best way to separate out the components from the spectrum of what look like 1 dot of light and put it properly 2 dots of light. So it was a great deal of fun working with him, so I'm delighted that he's back here today. Since being at Georgia State, he went on to work in Poland in Warsaw at the Copernicus Astronomical Center, which is one of the great centers in the world for studying pulsating stars. And then a few years ago, he moved back to the United States to Penn State University, where he's now in the Center for Exoplanets and Habitable Worlds, working with Eric Ford, and he's studying at the moment how stellar granulation, that we study on the sun, how that affects both the photometric light curves and the spectroscopic analysis of the stars, so that when we start to look for other worlds, other Earths around other stars, we'll be able to set aside what part is the gyre from the star and what part is the signal from the planet itself. So he's doing some really exciting work. But today he's back to talk about his first love that he got going on here, which is binary stars and the asteroseismology of binary stars. So thank you, Joe.
Thank you so much, Doug, for the nice introduction. It's it's always a pleasure to come back. So my topic is actually about stellar positions, stellar oscillations in binary star system. So if you, it's not working? Okay. Anyways, they are pulsating. So the outline of this talk is that, so first I'm going to introduce Astro seismology, and then I'm going to serve you 3 entries. And the first one is how we can measure the rotation of the stellar cores for the A stars or F stars. And the second topic is about Hubble B stars, which are this binary star system with eccentric orbits and tidally excited oscillations. And finally, the third topic is about how binary star evolution with mass transfer can form different types of variable stars. And so in the end, if we have some time, I'm going to talk about, I'm going to serve you some dessert. It's about one of the closed binary systems that shows this tidally trapped oscillations discovered from tests. So what Astro seismologists do is that first we have some observations, like say Kepler light curve, we have some time series, flux and function of time. And then we check out the Fourier spectrum, which is the amplitude and function of frequency. So basically you find all these frequency peaks, each peak is an eigenmodel star. And we I want to find out what kind of oscillation mode it is, and want to identify the oscillation mode. So it's described by the alpha, theta, and phi. So the oscillation modes of stars are basically 3D standing waves, which can be described by this and function alpha, theta, and phi in the spherical coordinates. So in the radial direction, it's just like the oscillation on a string, and it can be described by the quantum number n, which is the radial order. So we have the fundamental mode, the first orbital mode, the second orbital mode. So for this one, there's n equals 0, which means there's no radial node between the two ends. And for this one, there's one node. This one has two nodes. And for the other two directions, theta and phi, we use the spherical harmonics, which is function of theta and phi, and described by these two quantum numbers, L and M. So this is a combination of different spherical harmonics with different L and M numbers. This cartoon is basically showing you that Astro seismologists live in the Fourier space. So if you give them a Fourier spectrum, they can stare at the Fourier spectrum for like hours. And well, this is the Kant actually. So what we do in Astro seismology is that we want to find pattern in the Fourier spectrum. So here, this diagram is showing you a Fourier spectrum for a P-mode pulsator, a solar-like oscillating stars, or a red giant. You can see this is the amplitude, this is the frequency. You can see all these frequency peaks are almost equally spaced because this is the high-order P-mode. They are equally spaced in frequency. So I have labeled all these peaks with the quantum numbers L, which is the spherical degree. So L equals 0 mode, the radial mode, L equals 1, the dipole mode, L equals 2 modes. So from the spacing between adjacent radial modes, let's say L equals 0 mode, and this one is also L equals 0 mode, the spacing between the adjacent radial modes is called the larger separation, which basically is a function of stellar density. And also the spacing between L equals 2 and L equals 0 mode is called the small separation. And this small spacing is a good diagnostic for stellar age. So down here, this is a different kind of pulsator. It's actually an A or F type gamma dwarf star. It's a J-mode pulsator, so pulsating with J modes. And this is the Fourier spectrum again, but this time this is amplitude, but this is pulsation period, not pulsation frequency. So you can see all these peaks is almost equally spaced again. If you plot the spacing between these peaks, you can find that actually the spacing, we call the period spacing, is almost a linear function of the period, or pulsation period. So from this period spacing and period diagram, we can actually determine the rotational stellar core, because this kind of gamma dwarf stars have the convective core in the center. So, so this is the pulsating HR diagram, and so you can see this is the main sequence. This is a white dwarf cooling track. So I have scaled animation, so then it's proportional to the oscillation frequency. So you can see on the white dwarf cooling track, we have at least 3 types of pulsating white dwarfs. On the main sequence, so on the upper main sequence, we have 2 types of pulsating B stars called the beta Cepheid star, the massive B star pulsating with P modes, and the slowly pulsating B stars, SPB stars pulsating with J modes. And again, but most relevant to this talk is this A or F type stars down here. It's a dead Scuti star or gamma dwarf star. There are 2 different types of pulsating stars. And also here, the sun and other stars like the sun, solar-like stars, they are pulsating with pressure modes, high-order pressure modes. Also the red giants also are showing this solar-like oscillators. So these 2 dotted lines, this is a classical instability strip. You can find the Cepheids, the radial pulsator, and the R. Lyrae star here. So, the first topic is about how we can measure the rotation of the stellar core from Astro seismology, basically with G modes. So let's go back to this Fourier spectrum again. So actually from the period spacing and period diagram, we can measure 2 parameters at least. First one is the near core rotation rates. This is because the pulsation period or J modes is the most sensitive to this near core region here, to the chemical gradient region here. So this is a stellar surface, and this is a convective core. And the second parameter we can measure is it's called asymptotic period spacing. It is actually a good diagnostic of stellar age. It's actually an integral of the Brunton stellar frequency, which is a function of the chemical gradient here. So I already mentioned we can measure the core rotation rates. So we can do this for binary stars. So we have picked about 80. We have picked all the Kepler eclipse binaries with position components that show this kind of gamma dwell positions, the GMO positions. Basically, we are trying to find patterns in the period, so in the Fourier spectrum, in this amplitude versus position period diagram. So you can see this Fourier spectrum has many position frequencies which are almost equally spaced. So we fit the Kepler eclipse, the eclipse binary line curve, this red line, and then we subtract them, and then we check out the Fourier spectrum of residuals. So I'm going to show you one binary star called KIC 959. This is a Kepler eclipse binary which has two partial eclipses, and also this is a radial velocity curve. So we have derived the fundamental parameters like the mass, the two A stars, and radius and temperature. So this one has an optical period of 1.2 days. So in the Fourier spectrum, we find that, so this is amplitude again, this is the frequency. We find this star is positing with both P modes and G modes. And for these G modes, we identify them as L equals 1, M equals 1 G modes. And we find that these G modes are also equally spaced. And from the spacing and the slope of this spacing, we can find that the surface and the core have the same rotation rates, which have the period of 1.2 days. So it means both the surface and the core has been synchronized with the binary orbit in this closed binary system. Also, by the way, if you guys have any questions, I would like to answer them. You don't have to wait for the end of the talk, I guess. This is another Kepler eclipse binary called KIC 7385. Again, this is the Kepler line curve. This is the Fourier spectrum. And these guys are also L equals 1, M equals 1 G modes. And we find that if we plot the spacing between these peaks and the function position period, we find the slope. And this slope, from the slope, we can measure the near core rotation rates, which is 0.64 cycles per day, which is almost the same as the optical frequency with 0.61. So this is, again, another synchronized system, synchronized gamma dwell star in binary star system. So we have done this for about 80 gamma dwell star in Kepler eclipse binaries. Yes?
Oh, sorry. In the previous slide, just checking, is the flux over 1 is the signature of the pulsation of the star? When it got
No, this is ellipsoidal variation.
Okay.
Yeah, so I think that when you plot the line curve, you just normalize the line curve by either the mean or something.
Right.
So this is 1. So if you fit a binary line curve like this and you subtract them, and it's tiny residuals, these tiny oscillations are these oscillations here. So, yeah. So I was back to this diagram again. So we have done the same thing for 80 gamma dwell stars in binary star system. So this is the plot. This is the ratio of the optical period and the core rotation period. So so 0 means the core rotation, the optical period and the core rotation period is the same. So you can find that this is the optical period. You can find that for binary star system with optical period less than about 10 days, 1 about here, this ratio is almost 1. And for binary system with longer optical periods, the core are not synchronized. So this is actually, so this color-coded is the asymptotic period spacing. So pi 0 is asymptotic period spacing is the integral of the Brown-Van stellar frequency. So if this parameter is actually a diagnostic of stellar age. So if we plot this parameter from 0 edge main sequence to terminal edge main sequence, it looks like this. Basically, it's like a monotonic decreasing function. So it means for this sample of star, we can actually have some constraints on stellar age as well. So this is for binary star system. So if we compare the core rotation rates with or gamma dwell star in binary star, and compare this with single gamma dwell stars, so this is a histogram for the rotation rates, the core rotation rates of single gamma dwell stars, about 600 stars. So basically, most of the stellar cores rotate at about 1 cycle per day here. And this is the same as this yellow histogram here. And the gray histogram is the core rotation rates of gamma dwarf star in binary star system. You can see that in binary star system, we have more slowly rotating cores. This suggests this is kind of the result of tidal interaction, the tidal synchronization from the surface all the way to the core. So this is actually a good sample to study the ongoing momentum transfer inside the stars. Now it's time for the second topic, which is about tidally excited oscillation in the heartbeat binary star system. So the oscillation that I talked about so far is free oscillations. It means this student can work. So basically, the oscillation equation is AX equals 0. But if in the binary star system, if you have a tidal force from the companion star, you can also drive the tides can also drive this student to work. So basically, if the supervisor drives the students will work at the pace of the driving frequency. So then this force stellar oscillation equation will become AX equals B. So B here is the tidal force from the companion star.
Is that really how it works? Because in our group, the students are doing all the driving. The advisor just sort of...
Well, you can swap this too, I guess. The prototype for this kind of heartbeat star system is called KY54. I think it's discovered back in 2011. So I have a video here. I think so this is a binary star system. It has a face-on orbit with two A stars, main sequence A stars, in a very eccentric orbit with eccentricity of 0.8, of the period 42 days. You can see this is a Kepler-like curve. You can see this. There is a periastron brightening and periastron passage here. You can also see this strong oscillations, which are the tidally excited oscillations. Actually, these two dominant oscillations are exactly 90 and 91 orbital harmonics. So they are L equals 2, M equals 0 moles. So after this KY54, Kepler has discovered about 160 heartbeat stars, and about 1/4 of them, maybe 1/5 of them, show this kind of tidally excited oscillations. For example, this one and this one, these guys. So I'm pretty interested in this kind of binary star system with oscillations. So we studied this one we call KIC 323. So similarly, these are two A stars, but in an adjunct orbit. But this is a Kepler-like curve, phase-folded. There is an eclipse near periastron passage, and also it's a very the eccentricity is 0.6. It's a very eccentric orbit. You can also see this oscillations in this phase-folded light curve. That means these oscillations are orbital harmonics. In the Fourier spectrum, we find that all these peaks, frequencies are almost orbital harmonics from, let's say, 10 times the orbital frequency to 21 times the orbital frequency. So in order to model this kind of tidally excited oscillations, there are at least two methods to model this kind of oscillations. The first method is to decompose the tidal response of the star, let's say the displacement vector, into a linear combination of the free oscillation eigenfunctions, and the sum is respect to the n, l, and m. And each mode has different amplitude C alpha here. So this idea is similar to the idea that any image on a stellar surface can be decomposed into a linear combination of spherical harmonics. So you just sum L and M. So if you don't believe me, I have decomposed Doug's image into spherical harmonics. So you can see by adding more and more spherical harmonics, we can approximate this image pretty well. So the second method is actually to directly solve the forced stellar oscillation equation, AX equals B. We just add this tidal potential to the momentum equation. So we have changed the gyre oscillation code, which I will mention later. So we have some results here which shows you the Lagrangian radial displacement vector for the real part, for the imaginary part, we have compared our code called JR false with another code called caffeine. They show very excellent agreement, but our code is 1 order of magnitude faster. So if you have a smartphone, you can actually scan a QR code here. You can find a tutorial page showing you how to use the JR false code. They will teach you how you can configure the input file, let's say the orbital parameters and what kind of mode you want to calculate L equals 2, mostly, M equals something. And also what is the eccentricity, what is mass ratio, etc. So from this code, we can actually also simulate the light curve. So this is a simulation for the light curve or another Hubble star system called Iota Auranis for different inclinations. And this diagram shows you the evolution with the orbital parameters. Let's say the centimeter axis, the eccentricity, because it's the secular evolution with this orbital parameter depends on the tidal parameter on the stellar surface. So from this oscillation code, we can actually directly get this kind of secular evolution for binary systems. So now we know how to model these oscillations. Let's go back to the KSA 323. So this is the magnitude of the oscillation. This is the dropping frequency, the orbital harmonics. All these color symbols are just observations, observed tidally excited oscillation in this binary. All these diamonds are our models. You can see pretty much our model does a pretty good job in fitting all these observations because it suggests this oscillation of L equals 2, M equals 2 prograde modes, or magnitude, depending on your definition. We also model the position phases. So this is the orbital harmonics. This is the phase. So if the oscillation is adiabatic, they will align with this green line here for M equals -2 mode, and this line. You can see the observations almost align with this theoretical prediction. So we can also identify the position modes from the position phases. So after this binary, we have a few other binary star systems. This is similar system to KOI 54 called KIC 90616. This is again a Kepler light curve showing you the phase-folded light curve, and this is a pi-Astron passage, and also there's the strong positions. This is also a phase-on orbit. And the Fourier spectrum shows one dominant positions, which are 24 times optical frequency. And the position phase agrees with M equals 0 because it has a phase of 0.27, which is essentially within 1 sigma of the L equals 2, M equals 0 mode. The theoretical prediction is 1.25. And this is yet another binary, Hubble star binary, KSC A719. The Fourier spectrum shows 2 dominant oscillation position mode. So they are 26 times optical frequency and 29 times optical frequency. And this binary is actually A star with the M star companion. It has a grazing eclipse actually. So the position phases of these 2 modes, this one has a position phase close to M equals 0, and the 29 optical harmonic has a phase close to M equals 2. So actually, there are some other Hubble star system that's more complicated. For example, this one KSC 4142. So this is the Kepler light curve with eclipse and pi-Astron brightening or hump, ellipsoid variation. And this is the radial velocity from the Keck high-rise spectra. So we have measured the mass and radius of the 2 stars, which basically the 2 stars have similar masses, which are 2.0 solar mass. So this is the Fourier spectrum. We find that in the low frequency region, this is a mixture of intrinsic gamma dot type G modes and tidally excited G modes. There are 2 types of G modes. All these gray squares are the tidally excited G modes, which are optical harmonics, and the rest are essentially gamma dot type G modes. And in the high frequency region, we have Delta-Scuti type P modes as well. So this is a hybrid pulsator. So again, we try to model the position amplitude of these tidally excited oscillations, the TEOs. So there's a tricky part is that because the position amplitude depends on the frequency detuning parameter, which is the difference between a driving frequency and the eigenmodel star. So if you change your stellar model by, let's say, 0.1%, you will significantly change the detuning parameter. So we have to treat this parameter as a random variable, and we can calculate the position amplitude in a statistical way. So here I'm showing you the observations, the squares of observations, and the shaded region are the plus minus 2 sigma of our calculated amplitude. You can see they are pretty much, the other observations pretty much lie in this plus minus 2 sigma region for L equals to M equals to prograde modes. And also we can model the position phases. So again, this is a position phase in units of 2 pi, 0 to 1. And this is the orbital harmonic. So if the positions are adiabatic, all these position phases should align with this red lines here, the 2 red lines. So this is, so the observations are the squares, and the blue dots are our models. You can see for the high frequency part that they show pretty nice agreement, but for very low frequency G modes, because of the radiative diffusion in the stellar interior, it will show a strong adiabatic effect, so there will show some deviations here. So, okay, so this is my third topic. It's about Positron stars that can be formed from binary star evolution with mass transfer. So let's go back to this Positron HR diagram. So what is missing in this picture? So I already mentioned the tidally excited oscillations, which is missing here. But another thing that is missing is because this is based on single star evolution. So this is all evolution tracks are single star evolution tracks. So if you consider binary star evolution with mass transfer, you can actually form different type of variable stars. So, so if we start with 2 main sequence stars in a closed binary system, and depending on whether the mass transfer is stable or not, you can actually have different channels, the formation channels. This binary star evolution mass transfer can generate many different kinds of binary stars, like algo system, X-ray binaries, blue stragglers, substar stars. So this is actually, no one has checked whether this kind of process can form pulsating stars. So this is kind of the frontier still. So I will focus on this stable mass transfer channel here, which can form the algo system or blue stragglers. So when in this channel, when you can form algo system, but for the low mass algo systems, there is one type of variable star, binary star called ELCVN binaries. So basically, it contains a or F type dwarf star, is a mass gainer, and a very low mass helium Y dwarf precursor, which is a mass donor. So, so I have used the Mesa evolution code to run the simulation and check how this kind of binary star can be formed from the two precursors. So, so I have started this simulation with m equals 1, so m1 equals 1.35. So the more massive star here will evolve along this white evolution track here. So it will fill its rho slope here when it is a subgiant, and then it will transfer mass to its companion M2, and then this evolution track will evolve downwards to the lower luminosity region, and in the meantime, the mass gainer will accrete mass. It will become more massive and more luminous, and evolve along this red line here. And so actually, when the secondary star, when the M2 is accreting mass, it is rejuvenated. So it's called newborn star. It looks like a zero-edge main sequence again because this red line is essentially in parallel with this zero-edge main sequence strip here. So this stable mass transfer will continue until the point marked by this star symbol here. And then the mass donor will evolve into a long-term constant luminosity phase and slowly contracts and becomes a helium Y dwarf here. And here, this is a Y dwarf cooling track. And the mass gainer here will evolve into a higher luminosity region. It will actually evolve into this dead Schooley instability strip and begin to show pulsations. So it means this binary star evolution with mass transfer can form pulsating stars. So we have studied one of the Kepler eclipse binary like this, called KIC 826. Again, this is the Kepler light curve. This is the residuals. The light curve shows 2 partial eclipses, and also strong positions here from the primary star, which is a Dead-Scuti A-type star. And the radial velocity shows that the 2 stars have different masses with a mass ratio of 0.1. So if we check out the fundamental parameter that we get, we find the primary star has a mass of 1.94 and the radius 1.67. So it's a typical zero-edge main sequence A star. The M2 has a mass of 0.2 and the radius of 1.31. So we know that the universe is not old enough for a 0.2 solar mass star to evolve into a giant. So this binary star must be formed from binary star evolution with mass transfer. So this secondary star is a helium white dwarf precursor. So if you check the Fourier spectrum of this binary, it actually shows high frequency positions at about 60 cycles per day. And this is from the primary star, the A star. For this A star, the Dead-Scuti star, if the star is young, it will show high frequency positions. As the star evolves, it will show low frequency positions. So if we start the evolution, let's say 1.9 solar mass star, this is the HR diagram with the evolution track. You can see if we start the evolution at a zero-edge main sequence, you can see this is the theoretical oscillation frequencies, and this hump is the place where we can drive the oscillation modes. So for the zero-edge main sequence star, the positions are driven at about 60 cycles per day, high frequency. If we evolve the star, the oscillation will shift to lower and lower frequency. And then after the central hydrogen exhaustion here, the star will evolve into this hook. In this short period of time, it will contract. And then this position frequency will shift to higher frequency for a short period of time. And then after the contraction, it will shift to lower frequency again. So this suggests, if we go back to the observations, it suggests that for this Dead-Scuti star to show high frequency position, it must be very young, must be close to zero-edge main sequence. So this agrees with the scenario that this is a mass-accreting star rejuvenated from the mass transfer. So actually, let's go back to this formation for the binary. The mass gainer actually can evolve into SPB instability strip, the slowly pulsating B star instability strip. So if you check out the histogram, the mass histogram for mass gainer, you can find that the mass gainer can be as massive as 2.5 or even 3 solar masses. So you can evolve into a B star and show this slowly pulsating B star again. So we indeed find such a slowly pulsating B star in Kepler. So this is KY81, which has a B star primary and white dwarf companion. And this is the Kepler light curve. This is the Fourier spectrum, which shows the low frequency J mode position, which are retrograde J modes for this B star. So I have talked about the mass gainer, but what about the mass donor? So when the mass donor evolves into this constant contracting phase, it can actually, it is called the extremely low mass white dwarf precursor. It can actually pulsate with P modes or J modes. And later, when it evolves onto the white dwarf cooling track, and it will evolve into an extremely low mass white dwarf and show J mode positions. So it means this formation channel, the mass donor can also, you can actually form 2 types of variable stars for mass gainer, for the mass donor, and the white dwarf precursor and the white dwarf here. So I have listed all the post-mass transfer pulsating stars. So I already mentioned in the formation of ELCVN system, we can form the Dead-Scuti star pulsator, gamma dwarf star pulsator, or slowly pulsating B stars, as well as the extremely low mass helium white dwarf and its precursor. But there is also observational evidence for the post-mass transfer RL Lyrae star so in a binary star system. they find that the mass is 0.26, the dynamical mass, which is much lower than a typical R-Lyrae star, which has a mass of 0.6. And this suggests it's probably from binary star evolution with mass transfer. And there's also a anomalous Cepheid in binary stars, and it has a mass of 1.5. And really it's 25. It also seems to be formed from binary star evolution with mass transfer. And there's also a new type of variable star called the BLAP, the Blue Large Amplitude Pulsator, which is probably also involved binary star evolution. And we know, of course, we know subdwarf B stars can be formed from binary star evolution. And in the end, there must be some other type of variable stars that can be formed from this process. So if we put all this post-mass transfer position star on the HR diagram I have shown you before, this is a very tentative post-mass transfer pulsating HR diagram. So we already know the B stars, A stars, and also Cepheids, R-Lyraes, extremely low mass white dwarf, and its precursor, BLAP, subdwarf B stars. So this is really the frontier, and people have been, and I think no one has checked this kind of formation process for pulsating stars, except for the Cepheids. So, okay, now it's time for some dessert. So we have found a binary star system called HD 74423. So it's a closed binary system with a 1.2 orbit, day orbit. The primary star is a dead Scully pulsator pulsating with p modes. And we find that the positions have a much larger amplitude in one hemisphere than the other. So why is this happening? Because let's say this is the ellipsoid variable. So this is the test lie curve. There's this sinusoidal shape from the ellipsoidal variation from the tidal deformation of the star. So this is a binary model. The primary star is almost filling its Roche lobe. So when this is the inner Lagrangian point, the L1 point. So we find that when this L1 point is pointing towards the observer, it has a large pulsation amplitude here. But when it is pointing the other way, it has a lower amplitude. So this is a pulsation only. This is afterwards subtracting the sinusoidal shape. This is a residual. These are pulsations. So this is the first time we have ever seen a star that has a larger pulsation amplitude in one hemisphere. So the reason for this is that in this almost Roche lobe filling star, near the L1 point, the effective temperature will be lower here. And if the effective temperature is lower, the acoustic cutoff frequency will be lower. It means the P modes can actually, the acoustic waves can propagate closer to the photosphere and will create a larger flux perturbations. So, so you can essentially say this is a star that is pulsating only in one hemisphere. And because, so another feature for this binary is that, again, this is a model. This is the rotation axis. So this is the pulsation axis, which is pointing towards the companion star. So usually the pulsation axis should be aligned with the rotation axis. But for this one, because of tidal force, it's pointing towards the companion. And this is also the first time we have ever seen a star that shows a pulsation axis aligned with the companion star. So because of this, the position will be modulated when the star evolves, right? When the star rotates, right? So this is modeling for the P modes. The P modes will show the modulation, the amplitude modulation and the phase modulation, because this kind of oblique pulsator model. It turns out this oblique pulsator model can do a pretty good job for modeling this kind of modulations. Okay, so so I haven't finished my talk, but I want to advocate something. So this is a TESS Astroseismic Consortium website. So if you're interested in astroseismology, you can actually register to this website. There's a conference photo from the TASC or CAST conference this year in August from Cambridge. If you zoom in, you can actually see Rich Thompson and me. We are holding the jar sticker, the shamelessly advocating the code. But the important part is not the photo, but this part. So you can see we have different working groups, 1 to 8, working group 1, exoplanet hosts, 2 solar-like stars, 3 cast clusters, and 4 and 5 are AF stars or OB stars. This is a classical pulsator, the opacity-driven pulsator. And also working group 6, are Lyrae star and Cepheids. And working group 8 is the compact pulsator, the white dwarfs, SDB stars. So this is a very active community. And if you check out, let's say, working group 2, you can find a lot of ongoing projects. Say this is the leader, this is the email. If you want to join the project, you can just send an email to the leader, and then even you can only do some literature review or Fourier transform, some very basic data reduction. You can still contribute to this community, because the test is delivering data every month, and this is a very busy, very active community. So I suggest everyone who is interested in this to register this website. So this is the working group 4, which is a F star, A star working group. These are the proposed projects by different people. Okay, so this is my final slide. So the takeaway message is that stellar oscillations, we can measure the core rotation rates from stellar oscillations, and we can also, the binary star evolution can generate a new type of variable stars and also contaminate the old types. And also tides can excite stellar oscillations. And we also find a new type of phenomenon called tidally trapped modes. And last, pretty welcome to join the working group and this community. Okay, thanks very much. Yes.
Thank you very much. Questions?
Fascinating indeed. I have a question regarding to